Hello and welcome to the Daily Space for today, October 3rd, 2018. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. As always, this show is brought to you by CosmoQuest.org, and I'm going to say, if you've got extra screen real estate, if you've got extra brain cycles, go ahead and pop open CosmoQuest.org while you're listening to this show and help us map out the solar system. Go and mark craters on other worlds. Help us find the safe places to land a spacecraft and the interesting science that we need to explore. Now, the kind of science that we do at CosmoQuest is not the kind of science that makes up today's first story. This is a story that is, a tale of black holes. This research, which is coming to us from the University of California at Berkeley, is one that looks at the probabilities of various things happening to see if it's possible to rule out or rule in the likelihood that some theories are true. One of the things that regularly gets asked, including by many of you, is can black holes be, can they be what that dark matter that we can't see is out there? And many different reasons have been given as to why no, the majority of dark matter is not black holes. These arguments have generally relied on looking at things within our galaxy and within the environment of our galaxy. For instance, the Macho and Ogle projects both studied large areas on the sky to see if over the period of time they could detect the movement of black holes through our galaxy as those high mass objects passed in front of background stars and with their gravity bent additional light towards the Earth, essentially magnifying the light that we received from these distant objects. Well, what these projects didn't rule out was the possibility that maybe outside of our galaxy, maybe beyond our galaxy, there are a wealth of black holes out there that, maybe make up the majority of the intergalactic dark matter. In new research from University of California, Berkeley, instead of looking for stars to be brightened within our own system, they instead looked to see how often are distant supernova magnified by intervening black holes. In this research, they looked at 740 of the brightest supernova that have occurred since 2014. Because we know how bright supernova should be based on the amount of material that goes into the explosion, because we can measure where supernova are from their redshifts, we know how bright they should appear. Just like when you go outside and you see headlights off in the distance, you know roughly how far away that car is because you know how bright headlights at a given distance should appear. With supernova, we just do it much more mathematically than what you do, intuitively with your brain. Now, looking at all of these different supernova, they knew that if intermediate mass, or what we refer to often as primordial black holes. These are the black holes that aren't formed by massive stars ending their lives, the black holes that aren't formed in the centers of galaxies. If these black holes that may have formed in the early universe before we had stars and galaxies, if those black holes make up the majority of dark matter, we should see them actively getting involved in magnifying the light that we see from supernovae. And they looked at 740 supernovae, and they didn't see this kind of magnification. Now, this kind of research doesn't completely eliminate black holes as a source of dark matter. What this does is it puts a limit on how much of the dark matter can be made up of these intermediate black holes. Now, we didn't even know this kind of black hole existed until a couple of years ago, when the LIGO gravitational lens observatories began to observe the merger of these intermediate mass black holes. Now that we know they exist, we went looking to see, are these dark matter? And we can't rule them out as being not a part at all of the dark matter. We know they're at least a small part because we see them through gravitational lensing and through no other mechanism. And with this research, they're able to put the limits on how much of dark matter is made up of these primordial black holes. And the most they can be is 40% of the constituent dark matter of the universe. On the other end, though, they could be like 1%, 2%. All we know is the maximum amount of the dark matter that these primordial black holes can be is that 40%. This is cool research. It puts limits on these annoying questions of how much invisible stuff out there is, well, what would otherwise be fairly normal invisible stuff. And it still turns out that the majority of the stuff out there is stuff we don't know how to detect or define. Now, bringing things a little bit closer to home, I'm going to focus now on the Hayabusa 2 spacecraft, which is out exploring the asteroid Ryugu. This little spacecraft was launched back in December of 2014 on a mission to visit a nearby asteroid. This is what is called a near-Earth object. It is a roughly 1 kilometer across asteroid that has an orbit that brings it inside of the Earth's orbit around the Sun, but spends most of its orbit further from the Sun than the Earth. Because of its Earth-crossing nature, because it's close to us, it's easy to get to. And this is exactly what the Hayabusa 2 spacecraft did. When it arrived there in June, it carried with it a small fleet of little, tiny, adorable robots. The adorable is, of course, a personal opinion that we don't have an ability to scientifically quantify. What we can quantify is Ryugu is this extraordinarily rocky, crumbly surfaced asteroid that is really kind of amazing to look at, especially when we start to compare it to worlds like the much bigger Vesta and Ceres that look so radically different. This little boulder-strewn world is going to be explored for the next couple of years by Hayabusa 2. And as I said, Hayabusa 2 carried these little robots with it. These two, the first two of these little robots to be deployed were Rover 1A and Rover 1B. I use the term rover loosely. In this case, it's an acronym. The reality is that these are hoppers. These are two little tiny circular spacecraft that actually they're more like this big. You can put both of them in the inside of a standard Triboli or cowboy hat or pretty much any hat you might have around. Both these rovers will fit into. And they don't rove by rolling wheels and rolling around on the surface of their worlds. What they do instead is they have a little spring-loaded mechanism and they hop. This particular image was taken by Rover 1B while it was on the way down to the surface of Ryugu. Now, once the little spacecraft got there, well, of course, on the way, it had to take a selfie. This is a selfie where you can see a little tiny shadow of the solar-powered hopper. And again, you can see just how rocky, cratered, broken up the surface of this little world happens to be. Now, with Ryugu, we continue to have the chat went away. We continue to have the shadow showing, and then once these spacecraft landed, they were set up so that they would automatically hop around the world, jumping from place to place and acquiring data with no human intervention. This meant that, after this little spacecraft landed, it promptly hopped back up again And here you can see an image that was taken during the hop. This, in this particular case, is actually an image from rover 1A. So I did switch between rovers, between images. Now, because Ryugu has such weak gravity, these rovers, when they hop, are able to linger in the, lack of air. They're able to linger in the lack of air above the surface of the asteroid for 15 minutes. And as they linger in the lack of air, they're able to move about 15 meters in any direction. So these two little hoppers are doing their best to explore this asteroid. Now, looking back at it again, you can see this is a rock that is just covered in smaller rocks, dirt, dust, and debris. And the fact that there's so much small stuff scattered all over the surface is actually a really good thing. It is hoped, and we never count our samples until they're returned, that Hayabusa 2 is going to be able to pick up some soil, some rocks, and bring it back to Earth in December of 2020, completing this little spacecraft's 6-year mission. If successful, one of the future rovers will scoop up some samples, bring it back, and it will be parachuted down to Australia. This is a truly international mission. It's built by JAXA, working with collaborators all over the world. And it shows you just what can be done when people put their mind together, think creatively, and have $150 million. But if you think about it, $150 million, which is the price of this mission, is, in the grand scheme of solar system exploration, a very small price to pay to get so much amazing science back to the planet Earth. So that concludes my stories for today. And in a couple of hours, I, in fact, am going to do very much like Hayabusa 2's rock sample is going to do, and I'm going to head off to Australia. Tomorrow, you will have the Daily Space with Dr. Andreas Plazas, who will be your host both tomorrow and Friday. And we're going to work out our schedule of operations for next week once I, get some ground truth data on just what the Wi-Fi looks like down under. If you are in Melbourne or Sydney, I will be doing a variety of science talks. I invite you to come out and hear them. I will be talking about asteroids at Mount Burnett Observatory. I will be part of the Science on Top team, speaking at a library in Melbourne. And next weekend, I will be one of the speakers at the Australian Skeptics Association meeting. Show up, I will bring you science, and let's explore this universe together. Now, I'm going to be here for a few more minutes to take your questions before I hand this channel over to Dr. Matt, who will be teaching Astro 101 at hour. So I see that Fenring already has a question. He is asking, or she's asking, this is a he, is asking, with how much confidence can we assume that intermediate size black holes exist at all? Could it be that there are only two extremes? Well, few years ago, I probably would have said we have absolutely no idea, and my personal guess is, since we haven't seen them yet, they're probably not out there, and I would have been completely wrong. The detections that we're making with the LIGO gravitational wave detectors are pretty indicative that the only way to explain the detections we're making is with these intermediate mass black holes in a couple of cases. Now, it's possible that there are ways that they're getting formed that aren't primordial, that we just aren't certain of yet. But the fact that there are these new mass black holes being detected is something that I feel we can have great confidence in. As with almost everything in astronomy, it's a matter of probabilities rather than certainties, because we can't, other than with the most local rocks, go out and touch them. So I can tell you what the surface of Mars is like. But with everything else, I can tell you what we think is true, what we believe is true, what all of the evidence points as being true, but we could be wrong. Science, it's working towards the truth and knowing that there may always be more to the story to tell. So Graham is asking, if matter falls into a black hole, does it revert to what existed before the Big Bang? Don't know. We know absolutely nothing, and many cosmologists would say we can know nothing about what existed before the Big Bang because time itself didn't exist before the Big Bang. Now, there are some cosmologists out there, Sean Carroll being one, and I'd recommend you listen directly to what he has to say, that have hints of ways that we might be able to get some information from before moment zero. But beyond not knowing what there was before our universe existed, we also don't know what's inside of a black hole and can't. So you're asking if two things I can't define are the same stuff. And what I can say is conceptually, sure. We don't know what either of them are. And the not knowing is indeed identical for both at this moment in time. And that's a very unsatisfying answer. So looking to see what else is out there for questions. I'm actually not seeing any other questions, but I will admit I don't have a good scroll history. I had a refresh on my chat that occurred. Yes, Paranor, we do need to send an AI robot near a black hole, but we're going to have to wait hundreds of thousands of years potentially for one to get there and for the data to get back. So Henny is asking, do Einstein's equations have anything to say about it? No, in fact, Einstein was one of the first to acknowledge that within the event horizon, we don't have an ability to find out what's going on. And this was one of those things that caused him to be one of the many people trying to figure out how to move beyond, the limits of his own equations. Hello, Michael. We haven't seen you in a while. I hope you are doing well. It's always so good to see you. You were missed at the Astronomy Cast 500, by the way, Michael. So do we have any other questions out there? While you're typing them in, I will remind you once again, The Daily Space is a production of CosmoQuest. Check out this and all the other media shows that we produce and that we host through our collaborations with numerous content producers over at cosmoquest.org/365 days of astronomy. This is our daily podcast that aggregates together content, well, not just from this show, in fact, not from this show, but it aggregates together content from the Weekly Space Hangout, from Astronomy Cast, and many other productions. And it is another way that you can keep on learning science. So check it all out. And the Daily Space and all the other content that you can find here on Twitch is put together by the Astronomical Society of the Pacific, Planetary Science Institute, and Youngstown State University. Give our channel a follow and get notified whenever we go live with a new show. You never quite know what you're going to get. It could be a space launch or just your daily space news. So Paranor is asking, did I finish packing? I am leaving for the airport in 2.5 hours. And I'm going to admit I have not yet finished packing, which is why this particular episode will end sharply at 12:30. I hope you had a great visit to Vancouver. I fully know why you weren't able to make the AC 500, and we fully support your decision. I can still say you were missed. I am a master of packing quickly, and Susie has witnessed this more than once. The only question is, have I charged all my electronics? And I think for that, the answer is yes. Do we have any science questions? Science questions are always appreciated. Hello, Magnus Themer. I am glad to keep filling your brain day after day after day. We all need our brains to be refilled. And I have to admit, getting to put together this show gives me an opportunity to read through all that's going on, to pick the stories that I bring to you. And I'm just taking some of the information you have let me fill my brain with and passing it along. So thanks for giving me that reason to fill my brain with science. So Fenring is asking, do we know what kind of material Ryugu is made of? It is what we've referred to as a carbonaceous chondrite. This is a stony asteroid. It's not rich in iron, not rich in nickel, not rich in any of the cool stuff we might want to be going and mining later, although it may, of course, have helium-3. Mostly it's just plain old rock. It's the same kind of stuff that falls out of the sky on a regular basis and often explodes over cities like Chelyabinsk, Russia. If you remember the skyburst that happened back in Valentine's 2015, or the bolide that exploded over Botswana in June of this summer. So Henny is asking, when will Hayabusa bring a sample back? It will get back to the planet Earth, it's believed, or planned, not believed, it's planned in December of 2020. So we've got a while to wait yet. And that is going to be a busy year because we're going to have the OSIRIS-REx mission at the asteroid Bennu, and it will be beginning to bring back its rock as well. This is a new era in asteroid science where we're not just taking up-close images, we're not just letting our spacecraft rest on the asteroids when we're done exploring, we're actually bringing the rocks home. And what's cool about this is while space likes to rain rocks on our heads, the rocks that we get in the form of meteorites on the surface of our planet, we don't necessarily know where they originated. They got blasted with our atmosphere on their way through the atmosphere. They're not things of known origins that have been protected from harm. When we can go out and pick up a rock and bring it back, we know exactly where the rock came from. We know exactly what its situation was. And it doesn't have to get lit up by our atmosphere, so we get a better sample back to the planet. Michael Mayer is saying, surely Hayabusa 2 is bringing back samples because we are not really sure what Ryugu is made of. So there's a difference between being able to say, my countertop is granite, and being able to say what the constituent minerals are. And my countertops are not granite. My countertops are cheap 1950s linoleum. But if my countertops were granite, there's a difference between being able to say my countertop is granite and being able to say my countertop is made of this specific set of minerals that has this ratio of atoms, that when I look at the specific atomic abundances of things that would have decayed out of radioactive elements, that I see this number of parent and daughter particles giving us this exact age, and when I look at the gases included in the minerals, I get these oxygen ratios for the different kinds of oxygen. Those details, which are what we get excited about because they tell us about when the rock formed, how far from the sun it was when it formed. These detailed ratios, I don't know when I say my counter's made of granite. All I know is it's a block of granite that I can run through a mass spectrometer, that I could slice up if I didn't like it and look at underneath a microscope and answer those questions. When I say that Ryugu is a carbonaceous chondrite, it's kind of like saying it's made of granite. Carbonaceous chondrite and granite is not the same thing, but they're both generic kinds of rock. And the individual breakdown, the specifics of exactly what the ratios of the different molecules and atoms are, that is why we're going to bring a rock home. So we have to start somewhere. We classify our asteroids as carbonaceous chondrites, as stony asteroids, as nickel iron asteroids. And this is a generic understanding of what is the bulk property of the space rock. And what we want to know is what are the atomic abundances of stuff and things in the space rock. We'll get there. We'll get there. So Hanny is asking so she's saying that she saw in Slack that if meteors would be more or less impressive on Venus. So on Venus, the atmosphere is much thicker, so they would get slowed down much more, and they'd get slowed down rapidly at the top of the atmosphere, and I'm not sure if you could see that light from the surface. So I just don't know. Mars, you have much less atmosphere, so they're not going to get slowed down as much. You're not going to see as much of a flash. So they will be wussier there. So I think kind of we're the Goldilocks, because we can see the light as it gets radically decelerated and heated up in the top of the atmosphere. Whereas Venus, I think the light would get blocked. And Mars just doesn't have enough atmosphere to have that interesting kind of a light streak across the sky. So Side MT is asking, is each asteroid made of different materials? Everything in the universe is made of the same set of atoms. Those atoms form a given set of molecules. And so everything is made of atoms. But in general, how the rocks appear is a function of where they formed in distance away from the sun. So something that formed closer in is going to have less water trapped in, less volatiles trapped in the minerals of the asteroid. Something that formed further out will have more water trapped in the asteroid. The kinds of minerals that are able to form. So here we have, oh man, I am totally blanking on any minerals that are actually formed on asteroids. So if asteroids had water, you could have the formation of the mineral olivine, and it would appear in different ratios depending on how wet or dry the asteroid was. So we see the same kinds of minerals. We see the same kinds of atoms, but the ratios that we see things in is a function of distance from the sun, and there will be individual variations between rocks. One way to think about it is if you go to the local garden store and get a bag of gravel that was all quarried at the same place, the stones are all in general made of the same constituent stuff, but some are going to be pink gravel, some of them are going to be blue gravel, and even though they all came from the same place, there is variation from chunk to chunk. So Graham is asking, if they found a fossil in a rock, it would really pose a few questions. Yes. Yes, it would. And part of me is really hoping that we are able to find some itty-bitty little tiny fossils on Mars at some point. That would make my heart happy. Yes, bacterial fossils, fossilized bacteria mats, all those sorts of things. Those are things that we're probably not going to find, but I'd love to find on Mars. Thank you for the Science Hearts, Paranor. I can finally do my own heart. Not well, my wrist does still hurt, but it's getting better. So we are out of time, and I have a plane to catch after I finish packing. Thank you all for being here, and come back tomorrow when Dr. Andreas Plazas will host the Daily Space. We are, as always, at 1 p.m. Eastern, 6 p.m. London. That is, if I'm doing my math right, 10 a.m. Pacific, Monday through Friday, most days of the year. So thank you, and give us a follow if you want to find out when we're going live. And we are supported through your subscriptions, and every bit really matters. So thank you. And wherever in the world you may be, have a fabulous morning, evening, afternoon. And remember, thank you for the bits. Thank you, Trekker Kev. And wherever you may be in the world, remember to go outside and look up. Bye-bye.